Good morning to all.
Good morning, sir.
Good morning.
Morning, sir.
Yeah, we'll start the presentation in just 2 or 3 minutes. So kindly await. Yeah, good morning to all. I hope the presentation is visible to you all.
Sir,
Yes, sir.
Thank you for your valuable feedback. So in today's presentation, I'm going to explain you about the satellite communication unit number 2. So where this unit is divided into two different parts. One is space segment and second one satellite link design. So first of all, we'll see this what is a space segment is. So this unit is entirely divided into two presentations. So the first presentation will be completely on space segment, and in the second presentation we'll be seeing the satellite link design and its effects. What are the drawbacks available? What are the effects due to this satellite link designing? Or what are the factors to be considered while designing an efficient satellite that is to be placed in orbits for specified applications? Okay. So let us start with the space segment. So what is a space segment? Obviously, we are familiar with the term called satellite. Satellite is an artificial body or a natural body that revolves around a mass or a body which is having mass greater than it. So we place artificial satellites in space for acquiring information, for getting data, or to know about the Earth's sphere, or to know about the particular planet's information, how it is, what is the color, what is its terrestrial, how much amount of water is present, what are the different informations available on different planets can be acquired through this satellite. So basically the satellite which is being placed in orbit will give us some information. So the uplink information is from the Earth to the satellite, and the downlink information is from satellite to the Earth station. So altogether the communication that takes place with the help of a satellite, we call it as a satellite communication system. So which is being classified into two segments. One is a ground segment, second one is a space segment. Okay. So what is this space segment is? So this space segment will consist of satellites which are used for TTC, so which is telemetry, tracking and command. Okay. Space segment is that it is present in space, having satellites in operation, having a connection with the Earth station, which are meant for TTC, telemetry, tracking and command. We'll see this. What is this TTC is also. So the space segment. So the space segment has buses as payloads that are present in the satellite. So what are we put in the satellite for acquiring signals and retransmitting the signals are being done with the help of payloads. So payloads refers to equipment that provide the service for which the satellite has been launched. So what type of service that the satellite is providing is being done by a payload in the satellite. Okay. Here we have another unit or another equipment present in the satellite, which is bus. So this bus does the function of connecting all the subsystems inside the satellite. So as we have in our microprocessor, microcontroller, we have buses, address buses, data buses, and so on, which are meant for connecting different units in the microprocessor. Similarly, we have in the satellite a bus, which refers not only to the vehicle which carries the payload, but also to the various subsystems which are required for the particular service. So depending upon the service, the number of buses may increase or may decrease, and depending upon requirement, it may vary. So connecting all the units in the payload, connecting all the subsystems in the satellite is what is the function of a bus. So payload and bus are the equipments present in your satellite. And this satellite is a part of your space segment. So coming next, what is present in your space segment? So in a communication satellite, the equipment which provides a connecting between satellites transmit and receive antennas. Okay, connecting between satellites transmit and receive antennas is called as transponder. This transponder plays a major communication link between the transmit and receiving address. So this acts as a repeater or an amplifier or a booster, as we do in our terrestrial systems. Okay, as we have a booster at our nearby locations. So that booster, what it will do is that it will receive the signals from a base station or from the user station, and then it retransmits. So the same this antenna does in satellites. It acquires signals or information from the earth station through the uplink frequency, and then it amplifies, repeats, and sends to the ground station again at a different location. So through the downlink frequency. So acquiring signals from earth station through uplink, amplifying, repeating, and sending to receiving antennas in the receiver earth station is the major function of this transponder. So this transponder is one of the main section of the payload, as it acts as the connecting link. It is the communicating link and the connecting link. Next is the subsystems in your space segment. So the first subsystem present in the space segment is your power subsystems. Obviously, when we launch a satellite, it requires power throughout its entire life. So depending upon the power available, also the satellite's lifetime is being decided. Second is the attitude and orbit control subsystems. Attitude and orbit control subsystems. So how the satellite should rotate, in which direction, in which orbit, and which attitude is to be decided by this orbit control subsystems. Third one, third one is the telemetry tracking. Yeah, the spacecraft subsystem. So the spacecraft subsystem is a part of your space segment having power subsystems, which has the period of life period of the satellites depending upon the power available. If the power drains, solar panels will be helping that. So all those are the function of a power subsystem. Second is the attitude and orbit control subsystem. So the orbital issues and how in an orbit the satellite should rotate in which direction, in which altitude range is the main function of your attitude and orbit control subsystem. Third one, telemetry tracking and commanding subsystems. So telemetry is that acquisition of data for which service this satellite is being proposed or for which purpose this satellite is being launched. So acquiring that information is the function of your telemetry, and continuous monitoring of that purpose is your tracking, and control over that is your command systems. So TTC, telemetry tracking and command systems. Fourth one is your communication subsystem, which has your transponders in it, and we have the main link between the Earth station and the space stations. The connectivity between them is being done by antenna subsystems. So let us see in depth about the power supply for the satellite system. Just a minute. So to see about the first topic of spacecraft structure or the spacecraft subsystem is your power supply. So the primary electrical power for the operating of the electronic equipment is obtained majorly from the solar cells. Why? Because the satellites are being placed in space, they require power to operate for a life period of about 10 years or 20 years or 30 years. So whatever the power which is being sent along with the rocket will have only a short period of duration. So in order to run or in order to supply power throughout the lifetime of the satellite, there should be adequate power for operating of the satellites, or the meaning of launching a satellite is waste, or when we had launched the satellite which is working for only 10 or 20 days is of no use. You cannot acquire the desired information. So power plays a major role in the working of the satellite. So every satellite would be equipped with solar power panels, which will get uh, heat energy from the sun, then convert into electrical energy and store in some batteries. Then, depending upon the requirement, the batteries will supply to the satellites different units. Okay, where individual cells. Typing mistake. I'll check it. Yeah, the solar cells which are being placed in panels, are individually placed. So individual cells will generate only a small amounts of power. Therefore, array structures of cells in serial and parallel connection are required for the desired power supply to the satellite. So the solar cell panels for an HS 376 satellite is shown in this diagram. You can see the right corner we have the solar panel which are being placed of arrays. You can see here the bottom, and HS 601 communication satellite, which is manufactured by Hughes Space and Communications Company. So this is an diagrammatic uh, illustration of how the real solar panel is present, which is sent for space along with the rockets and connected to your satellite system. Okay, you can see panels which are meant for supplying power to the satellite. So what are the dimensions? Let us see. So the spacecraft will be having a dimension of 216 centimeter in diameter and 660 centimeter long when it is fully deployed in orbit. So when the power supply or the solar panel which are being present in the orbit which revolves around the earth, the spacecraft will be about this dimension. So during the launch sequence, the outer cylinder will be telescoped toward the inner one to reduce the overall length. So all the solar panel would be submerged into a wing. So when required, it will open itself by motors. So at the beginning of life of the power supply, the panels produce 940 watts DC power, which may drop up to 760 watts at the end of 10 years. So initially, when the panels are being launched in satellite in space, they provide 940 watts of DC power, and which may be reduced or which will go down eventually to 760 watts at the end of 10 years. Since the life of each and every satellite which is deployed in space is considered to be as minimum lifetime of 10 years. So what happens during solar eclipse? We'll see that. So during an eclipse, so which are illustrated in unit 1, the power to the satellite is required. So the solar panels will be moving into a position which comes under the shadow of the earth, sun, earth and satellite in a same region. Okay, so the earth shadow will eventually fall on the satellite for 23 hours. So during that time, the solar power will not work out. So there will be an additional batteries which will be present inside the power supply, which are two nickel cadmium long life batteries that can deliver up to 830 watts, which can withstand about 48 hours. Okay, so during eclipses time, this long life batteries of nickel cadmium will supply power to the satellite for working. So at the end of life, at the end of life means after 10 years, the battery recharge time would be less than 16 hours. Initially, it will provide 48 hours. So as the days goes on and maintenance, the battery life will last only for 16 hours. So high powers can be achieved with the solar panels arranged in the form of rectangular solar cells. So the solar cells must be folded during the launch phase in order to avoid missed tragedy during the launch of the vehicle. And it during launch it will be folded, and during placing in the orbits in geostation it will extend just like the wings. Communications company, the solar sails were arranged to rotate to track the sun. As the earth rotates in its own axis, the satellite also will rotate in its own axis. So the solar sails will automatically tend to rotate depending upon the rotation of the sun, such that maximum power can be acquired, just like our sunflower. So as we are having a sunflower, in the morning it will be facing towards east. In the afternoon, the sunflower will be facing at the top, and evening it will be facing towards west, and it will put down its head in the evenings at the nights. So again morning it will rise. So in the same fashion, the solar sails are arranged in such a fashion to rotate to track the sun. So wherever we, depending upon the sensors will be put up for that. So this solar cells are capable of having greater power output than the cylindrical arrays, which are having a comparable number of cells. Okay. So this HS601 can be designed to provide an approximate of DC power 2 to 6 kilowatts in addition to the cylindrical arrays. And as I had said earlier, the eclipses. So since the eclipses will have an appropriate period of 23 days before and end after the equinox for both the spring and autumnal equinoxes, two NiH2 instead of cadmium nickel, NiH2 batteries are used in Hughes HS601, and this was mapped with Intel Satellite Service Series with Intelsat 6 and Intelsat 7 satellites. In order to give adequate power supply during the eclipses. So after the power supply, we are going to see about attitude control. Okay. So if there is any queries in the power supply, you can put in chat box. I'll give you 2 or 3 minutes. If there is if there are any queries, you can put in chat box. Yeah, is there anybody named Gayatri in your class, Susu? Susu is there? Sridevi?
Sir?
Yes, Sridevi.
Yes, sir. Good morning, sir.
Good morning. How are you?
Fine, sir.
How about joining this class?
Good, sir.
No, may I know how you joined this class?
Through the link, sir.
Who gave you the link?
Okay.
Understood, Sridevi?
Yes, sir.
What did you understood? What, ma? Nandini gave her.
No, sir. Sorry, sir.
No, that's what I'm wondering. Sridevi is more interested to attend my class. That can I take it? Or Sridevi is not interested in attending
No,
Umabadi sir's class? Umabadi sir's class?
like that, sir.
Yes, ma?
I am receiving 2 links, sir. So that's why I'm.
Oh, you are eager to join this class.
No, sir. Sorry, sir.
It is my pleasure that you are attending my class, but you will not get attendance if you attend my class because your number is enrolled in Umabadi sir's class.
Oh, yes, sir. Sorry, sir.
Understood?
Yes, sir.
No, no, have you understood the concept?
Yes, sir.
Okay, then that is enough.
Thank you, sir.
You can attend no issues. You can attend no issues, but I cannot give you attendance since you doesn't belongs to my class.
Okay, sir.
Yeah. Thank you.
Okay, sir.
So if no queries, I'll move on to the next subsystem, which is attitude control. So the attitude control plays another major role in the satellites. So in a satellite, most of the equipment are used for the purpose of controlling its attitude. So attitude refers to its orientation in space. For example, if you want to point towards a particular point on the earth, so the attitude is will be tuned such that the appropriate points will be observed or measured. For example, my satellite is focusing on a particular region of Thar Desert. So I should give instructions to the attitude control to focus on the Thar Desert. When does rain falls in the Thar Desert? How much amount of precipitation? What are the places with good vegetation? What are the places where no vegetation can be done in Thar Desert? What are the hilly regions? What are the mountainous regions? The types of rocks, the types of soils, all can be pointed using this attitude control. So the direction points can be done by using this attitude control in satellites. Okay. For example, in the case of Earth environmental satellites, which are much concentrating on capturing images of the Earth, and the Earth sensing instruments will cover the required regions of the Earth, just like you see in Google Maps with a satellite view image. Okay, for example, you want to see how the peninsular India is present. You can watch it. Wherever you have green color structures, it shows that you have a good vegetation. Where when you see brown or lightish brown, those regions are hilly regions. Where you find a blue color, those are water acoustics or water regions like lakes, ponds, irrigation canals, rivers, oceans, all. So this particular focusing on that particular point can be done by this attitude control. So in attitude control, a number of forces such as gravitational fields of the earth and the moon, solar radiation, meteorite impacts are referred to as disturbances talks that can alter the attitude. that alter the altitude. So due to the gravitational force of the Earth and the Moon, the satellite can be moving towards that. So just explain in unit 1, the oblateness of the Earth will lead to stable points and unstable points. So that plays a major role. Solar radiation. So when the sun comes to, when the satellite comes in between the sun and the Earth, the solar panels will be exposed to more amount of radiation or more amount of heat. So due to that, the solar panels will emit more radiation. And next is the meteoroid impacts. The celestial bodies or the meteoroids that are being placed in space, moving in space, will create disturbances in the direction of the attitude or in the motion of the satellite. Okay, so that has to be checked out. So attitude control must not be confused with the station keeping, since they are both closely related to each other. That I'll clarify you. Okay, what is an attitude control and a station keeping? So to find any deviation in the attitude control system, or not to find any deviation in the shift of position in satellite orientation in space, we will be having 4 sensors. What are the 4 sensors? Are that they are made up of IR sensors, infrared sensors are used, which are called as horizon detectors. Horizon detectors. So there would be 3 sensors deployed in triangular fashion and the other one in the quadrant fashion, one for each quadrant. Okay, and the fourth sensor will take the references values from all the 3 sensors with the center of the Earth as reference point. So 4 sensors will be placed in all the 4 different horizons along the satellite, and if there is any deviation in the attitude with respect to the Earth's center as the reference point, the deviation will be notified. So any shift in the orientation is detected by one or the other sensor. If one gets missed, the other will sense it, and a corresponding control signal will be generated, and we'll be having some motors to activate and restore its original position by using some restoring torques. Okay, the station keeping will send a signal from the Earth station intimating that this side there is a deviation of this much in east direction or west direction or south direction or north direction. So kindly move these many points towards this using a restoring torque. So usually this attitude control process takes place in the satellite automatically, but it is also possible for control of signals to be transmitted from Earth based on the attitude data obtained from the satellite. Okay, what I had said is an example of controlling from the Earth station, which is a station keeping. Then these controlling torques can be generated in a number of ways. One is passive attitude control and active attitude control, controlling torques. So let us see what is this passive attitude control is. For example, in Radio Astronomy Explorer 2 satellite, spin stabilization is often used. So here we will be using this passive attitude control. Okay, what is it is that the satellite stabilization is achieved without putting a drain on the satellite's energy supplies. Okay, so the types or the examples are spin stabilization and gravity gradient stabilization. where the gravity gradient depends upon the gravitational field of central body. So what is passive attitude control is that we will not be using any satellite's energy or the power supply. Without using that, the satellite will automatically spin by itself. Okay. The stabilization will be achieved by itself without putting any drain on the satellite's power supply. So which is passive attitude control. Coming to the active attitude control, there is no overall stabilizing torque. We don't have any overall stabilizing torque to resist the disturbances torques. So instead of that, corrective torques are applied as required in response to disturbance torques. For example, plus 2 degree deviation is there in your satellite. So that plus 2 degree, if it is unable to solve by the satellite itself, there are some methods to solve that which uses active attitude control torques. So the examples are momentum wheels, electromagnetic coils, mass expulsion devices. So that plus 2 degree in east or west or north or south, as an example, can be adjusted or can be stabilized by using any of these three methods or these three control torques. And this electromagnetic coil works on the principle that the Earth's magnetic field exerts a torque on a current carrying coil, and that torque can be controlled through control of the current deviation. So electromagnetic coil principle uses the Earth's magnetic field that exerts a torque on a current carrying coil, and this torque can be controlled through the control of the current exerting on that in equivalence to that plus 2 degree. So if that is being applied, so the satellite will move minus 2 degree towards the direction, towards the opposite direction which is being done, and it will nullify the effects. So we get stabilization, which is done through active attitude control. You can see in the diagram. Diagram A represents roll, pitch, and yaw axis. The yaw axis is directed towards the Earth center. You see here, yaw axis. The pitch axis is normal to the orbital plane, and the roll axis is perpendicular to the yaw plane and pitch axis. So this center box is your satellite. If there is any deviation in yaw axis, it will tend to rotate. In roll direction, it will tend to rotate. In pitch direction, it will tend to rotate. So if there is any deviation, appropriate torque will be given in opposite to that in order to restore its normal stabilizing functions. Okay. So RPY axis for the geostationary orbits. So it is diagram B. the four sensors will give us information about the positions with a reference to the Earth's center, which can be drawn in a 3-axis, which is roll, pitch, yaw, RPY axis. Okay. So these 3 axes defines a satellite's attitude controlling. So for an equatorial orbit, the movement of the satellite about the roll axis moves the antenna footprint north and south. Movement of the satellite about the roll axis, which is R. You can see that about this roll axis R will give the movement of the satellite about the roll axis moves the antenna footprint north south. The movement about the pitch axis moves the footprint east and west. And movement about the yaw axis rotates the antenna footprint. Next is the spinning satellite stabilization. So this stabilization is applied to cylindrical type of satellites. These satellites are mechanically balanced about one particular axis and then it is set spinning around its axis. So for geostationary satellite, the spin axis is parallel to north-south axis of the Earth. So spinning stabilizing technique. So this is your spinning mechanism. Approximately the spin rate is typically in the range of 50 to 100 revolutions per minute of the satellite. So this spinning is initiated during the launch phase by means of small gas jets. So these gas jets will tend to rotate the satellite in order to achieve the appropriate positioning or attitude controlling. So this is your diagram. We have North Pole and South Pole and the satellite is moving in an orbit. So we have the satellite spin using small gas jets. And the revolutions per minute will vary from 50 to 100. So the uniqueness of spinning satellite stabilization. So in the absence of disturbance techniques, the spinning satellite would maintain its correct attitude relative to the Earth. These disturbances are generated in a number of ways, both internal and internally to the satellite and externally to the satellite. So what are the internally generated disturbance torques and what are the external forces? Are that solar radiation, gravitational gradients, meteoroid impacts are the examples of external forces which gives rise to disturbances in the torques. Then what are the internal is that motor bearing frictions and the movement of satellite elements such as antennas also gives rise to disturbance torques which are internal. So these two internal forces and external forces can be corrected by using this spinning satellite stabilization in the absence of this disturbances torques. So the spinning satellite would maintain its correct attitude. The spinning satellite would maintain its correct attitude control related to the motion of the Earth. Okay. Either internally or externally. So in the spinning satellite stabilization, when the disturbances arise, that affects the overall spin rate of the satellite, will tend to make the satellite spin rate to decrease. and the direction of angular spin axis will change. The impulse type thrusters or jets or small gas jets can be used to increase the spin rate again and to shift the axis back to its correct north-south orientation. So all these thrusters, jets, small jets will be defaultly present along with the satellite system during the launch of your rockets. So one as a viewer need not bother about the designing. As a scientist or as an engineer, you need to bother about this satellite spinning. So nutation, which is a form of wobbling, can occur as a result of this disturbance torques, and which may lead to misalignment or imbalance of the control jets. So this nutation must be damped out by means of energy absorbers known as nutation dampers. So these disturbances externally or internally will make the misalignment of even the control jets, which is a form of wobbling called as nutation. So this nutation must be subdued or damped out by using some appropriate energy absorbers called as nutation dampers. So this is being used in your spinning satellite stabilization. So this is an example where an omnidirectional antenna is used. The antenna points along the pitch axis, also rotates with the satellite. Just an example of spinning satellite stabilization where a directional antenna is used, which is more common for communication satellites. The antenna must be despun, giving rise to dual spin construction. So you can see here an electric motor drive is used for despinning the antenna subsystem. Here at the top, image top, we have a electric motor drive. So this is an diagrammatic representation of a directional antenna that is used in satellite. Now I'll show you the HS-376 spacecraft. HS-376 spacecraft structure. How it was designed, what are the parts. You can see at the top a telemetry and a command antenna. At the top we have an antenna reflector, we have antenna feeds, so this point we have a despun repeater shelf, we have the TWT amplifier for amplification purpose or repeater purpose, and we have a thermal radiator which is used to control the power excess radiation. We have control thruster, you can see control thruster. Then we have battery pack, then we have a propellant, then we have the apogee kick motor, then we have solar cell arrays. So the solar cell arrays supplies power whenever the sun is present. So when sun goes or when the satellite goes into eclipse, the battery will operate. Okay, so this is structure of HS-376 spacecraft. So you can have a glimpse of this HS-376 spacecraft. Any queries, type in chat box. If you have any queries, put in chat box. After some 4 or 5 minutes, we'll resume. Hi Susu, how are you?
Hello, sir. I'm fine.
Yeah. Is there anybody Gayatri in your class?
Yes, sir.
Okay. She was attempting to join this meeting through her personal ID.
Okay,
So
sir.
kindly inform her to use official email ID.
Okay, sir.
So when she was entering into the meeting, I called you. You were not there. So I would like to give you the details also.
Okay, sir.
In the name of Gayatri Lover was the ID. So that's what.
Okay, sir.
Yeah, in C section there is no Gayatri, so I confirmed from you. Is there any Gayatri from B section?
Yes.
So inform the consent.
Okay, sir.
Okay. Yeah, is Kamal Teja available? Kamal?
Sir.
Yeah,
Sir.
congratulations, Kamal.
Thank you, sir.
Which one you are going to join?
Right now I'm not decided, sir. No.
Okay, okay. I think Mutuma sir is arranging.
Yes, sir. Sir. They had informed 2 days
Uh,
back, I think so.
yeah, yeah. You kindly have a talk
Okay, sir.
and choose which one would be appropriate for you,
Okay, sir.
depending upon your skill.
Okay, sir.
Yeah.
Thank you, sir.
So since there are no queries, I move further on from the HS 376 spacecraft. So the antenna subsystem consists of a parabolic reflector and feed horns mounted on D-spun shelf, which carries the communications repeaters, or we call it as transponders. These control signals and power must be transferred to the D-spun section, and a mechanical bearing should be provided appropriately. So the complete assembly is called as bearing and power transfer assembly. BAPTA, BAPTA. You can remember it like that. Bearing and power transfer assembly. So next we have the momentum wheels stabilization after the spin. Spin satellite stabilization, we have momentum. So certain dual spin spacecraft obtain spin stabilization from a spinning flywheel rather than spinning of the satellite itself. So these flywheels are termed as momentum wheels, and the average momentum is referred to as momentum bias. So this momentum bias operate at 0, and where was the system introduced is that it was introduced in the Intelsat series of satellites. Intelsat 6 series spacecraft are spin stabilized, all the others being 3-axis stabilized through the use of momentum wheels. So momentum wheel stabilization can be used in lieu of spin stabilization techniques, which uses flywheels or the reaction wheels for creating momentums. So after the attitude control, we are going to see the thermal control. Okay. Generally, the satellites are exposed to thermal radiations from the sun and the reflections from the earth. The satellites are subject to large and huge thermal gradients due to sun's radiation on one side, while the other side faces into space. So in addition to this thermal radiation from the earth's albedo which is the fraction of radiation falling on Earth, which is reflected, can be significant for low altitude and Earth orbiting satellites, LEO, low Earth orbiting and medium Earth orbiting satellites. The albedo effect will be present, whereas these are not present in geostationary satellites. Why? Because we will be placing the geostationary satellites which has the rotation of axis and speed with that of Earth. So it is negligible in geostationary satellites. But this Earth's albedo is the fraction of the radiation falling from the Earth, which is reflected only in low altitude and Earth orbiting satellites. So the equipment present in the satellite will also produce heat, which is to be removed. So the appropriate use of heat sinks may not be available for dissipation in space. So to operate the satellite in a temperature stable environment, the following considerations are to be done. Use of thermal blankets, radiation mirrors to remove the heat from communication payload. Heaters may be switched on when transponders are switched off. So these three considerations can be done such to avoid overheating of the satellite. If overheating occurs, the satellite will malfunction and it will send inappropriate data to Earth, where the Earth station relies on the satellite's information for manipulation and taking appropriate actions. Next comes the important TTC, telemetry, tracking and command subsystem. In short, we call it as TTC. So for the successful operation of a communication satellite, the TTC is also essential, where it involves both the Earth and space station. The main functions of the spacecraft management are to control the orbit and attitude of the satellite, to switch on off the communication system, to monitor the status of all the sensors in the satellite. So where the TTC plays a major role. So let us see what is this first T stands for. So first T stands for telemetry. Telemetry or telemetering is a function that can be called as measurement at a distance. Without touching or without physically touching or resembling, data can be acquired through some type of sensing, which we call it as a function of telemetry. So the data which are transmitted as telemetry signals include attitude information such as obtained from sun and earth sensors, environmental information such as magnetic field intensity and direction, frequency of meteoroid impact and many more. The spacecraft information such as temperature, power supply, stored fuel pressure, all can be dealt using this. information about the meteoroids or celestial bodies in space can be tracked through this often in response to the telemeter information. The information about the satellite, its functions or its malfunctions or its absorbed data is transmitted to the Earth from the satellite as a telemetry signal, and in response a command signal will be sent from the Earth depending upon the information received to the satellite, so which we call as command subsystem or the command function. So here is an subsystem of TTC diagrammatic representation. For example, we have a satellite. You can see this is a satellite which is ranging commands and telemetry, other telecast stations which is given to your ranging data. We have a TTC station at Allen Park, Ontario. Okay, TTC subsystem station. So from the satellite control center, some information is given to the data communication and reduction facility center with voice or data links, okay, which is bidirectional. So from there, the information is sent to analysis center or to a computer center. Okay, so this computer center is present at headquarters Ottawa. So TTC station at Allen Park, Ontario is your subsystem or a subquarters, whereas at Ottawa it is a headquarters which monitor and store the data. So the data are given to Eastern Hemisphere for transfer of orbits information only through the telemetry tracking and command facilities. So this is an example of that telemetry tracking and command system. So if there is any information which is malfunctioning, for example, the satellite says that the satellite is taking pictures of Mount Everest, for example. In Mount Everest, these many trees are present in summer season, and these many trees are present in winter season. These many trees are present in spring season. These many trees are present in autumn season. So this continuous data can be tracked. So if there is any hindrances, if suddenly from summer season to winter season, in between we have rainfalls. If rainfall occurs, the soil erosion takes place in Mount Everest. So the soil erosion will lead to degrading of the structure of Mount Everest. So that can be continuously tracked, and accordingly appropriate measures can be done. So this is just an example of Mount Everest. So anywhere in the world, the system is common. Whatever you want, you can track the happenings. So there are many sensors located on the spacecraft to monitor the pressure in fuel tanks, voltage and current in power in the conditioning unit, temperature in all the subsystems can be tracked, the status of each subsystem and switch positions, whether the switch is working, switch is damaged, which is over voltaged, power short circuits, monitoring the altitude control, whether it is present in correct orbit, orbital location, all can be done by using many sensors. So the data from all the sensors are given to the telemetry unit, and this unit digitize the data and transmit the data using FSK or PSK that you have studied in your digital communication subject. Frequency shift keying or phase shift keying method. So after telemetry, tracking of the satellite is a major factor. By having the satellite transmit beacon signals that are received at TTC and Earth stations. So tracking is important during the transfer and drift orbital phases of the satellite launch. Once it is on station, the position of a geostationary satellite will tend to be shifted as a result of various disturbing forces. So therefore, it is necessary to be able to track the satellite's movement and send correction signals as required. So if the position of the geostationary satellite tends to move +2 degree, there should be a shift in -2 degree. So that tracking of the satellite's movement and correcting that is the major function of this tracking of satellite. And the satellite range from the ground station is also required from time to time. So every milliseconds or every seconds or every minutes, the satellite movement is to be tracked. So this can be determined by the measurement of propagation delay of signals, especially transmitted from ranging purposes. So it is clear that the telemetry, tracking, and command functions are complex operations which require special ground facilities in addition to TTC subsystems aboarding the satellite. So the next important is the antennas or the repeaters or boosters, we call it as. Transponder. So the definition of a transponder is that it is a series of interconnected units which forms a single communication channel between receive and transmit antennas in a communication satellite. A transponder is a series of interconnected units which is meant for receiving and transmitting antennas in communication satellite. Okay. So the bandwidth allotted for this is C-band communication satellite service, which is about 500 megahertz, and this can be divided into subbands, one for each transponder, having the transponder bandwidth of 36 megahertz, where we have some 4 megahertz as guard band between each transponders. So we can allow up to 12 transponders in 500 megahertz bandwidth. Okay, so each transponder can have up to 12 such repeaters or 12 such amplifiers in the satellite in an accommodation of 500 megahertz in C-band. So next is the frequency reuse. I think most probably all are familiar with the term called frequency reuse, using of the bands that you had seen. 12 transponders are being used with 36 megahertz, so they can be typically reused for the purpose of polarization isolation. So reuse factors can be done. You can see a diagram which has horizontal plane and vertical plane. Okay. So the horizontal plane can be removed, only the vertical plane polarization can be set. So polarization isolation refers to the fact that carriers which may be on the same frequency but with opposite sense of polarization. It could be on the same frequency but with opposite sense of polarization that may lead to errors at your receiver side. So that can be isolated from one another by receiving antennas. Okay, that can be matched with the incoming polarization. So specifically we'll be using linear polarization. So with the linear polarization, vertical and horizontal polarized carriers can be separated. In circular polarization, left-hand circular and right-hand circular polarizations can be separated. So because the carriers with opposite sense of polarization may overlap in frequency. So this technique we call it as frequency reuse in satellites. So this is how the section of your uplink frequency and polarization plan is. So we have total 500 megahertz of bandwidth in C band. So we have guard bands in between 4 megahertz, 4 megahertz, 4 megahertz, and every 36 megahertz is used for one single transponder. So such that we'll have 12. Okay. So the frequency can be reused by using this spot beam antennas. You can see vertical polarization, you can see horizontal polarization. The frequency reuse can be achieved by spot beam antennas as they can combine the polarization reuse to provide efficient bandwidth of 2000 megahertz from the actual 500. So the existing 500 megahertz bandwidth can be increased up to an efficient bandwidth of 2000 megahertz. So this is a special function of a spot beam antenna by using this frequency reuse concept. Okay, as you had studied in your mobile communication, frequency reuse factor. So this diagram represents your satellite transponder channels. So from the receiving antennas, we have approximately 5.925 to 6.425 gigahertz. We have a band pass filter. So from the band pass filter, the unwanted signals above 5.9525, sorry, below 5.925 and above 6.425 gigahertz are being filtered out. We'll be using a wideband receiver, which again subduce the frequency to 3.7 gigahertz to 4.2 gigahertz. And we have demultiplexer 12. Why we choose 12 is that we have 12 transponders. So in each transponder, so this frequency will be sent with a power gain blocks of, and they are being divided with respect to its center frequencies in gigahertz: 3.720, 3.760, 3.800, 3.40, 3.880, and goes on. Okay, so in the output we have a multiplexer, which again does the function of reuniting all the signals into a single transmitting antenna at 3.7 to 4.2 gigahertz. Okay, so this is your uplink frequency. You can see at the beginning from receive antennas is your uplink, and here when we have to transmit antenna is your downlink. So always the uplink frequency will be higher and the downlink frequency will be lower. Okay. This is an example of satellite transponder channels. So to know about To know more about wideband receiver, I'll show this diagram again. And if you have any queries, kindly put in chat box. Then I'll proceed further. If you're having any queries regarding till this topic, you can type in chat box. Then I'll proceed further. So since there are no queries in the chat box, I move on to the next next slide. The wideband receiver. So always we have a duplicate receiver being provided. Why? Because if one receiver fails, what we will do is that we will go there and repair it. So instead of that, if one fails, the other will automatically switch on. So the duplicate receiver will be provided in such a provision such that if one receiver fails, automatically the other receiver will switch on. Okay. So this combination is referred to as redundant receiver, meaning that although two receivers are provided, only one will be used at a time. So this uses a first stage in the receiver called as LNA, low noise amplifier. This amplifier adds little noise to the carrier being amplified, and at the same time it provides sufficient amplification for the carrier to override the higher noise level present in the following mixer stage. So let us see the wideband receiver. So we have the input signals, and through the input filter they are being fed into preamplifiers. So we have the same duplicate receiver of that at the top. Okay, so if this receiver fails, which is at the bottom, automatically the upper receiver will work. So the preamplifier will be designed with an gain of minus 1.5 dB, and it is fed to a mixer with the oscillating frequency at 2.25 gigahertz. So they are being mixed up, and we get the gain fed to the amplifier will be of about 23 decibels, and it is amplified to 60 decibels and then to the demultiplexer unit. Okay, as we had seen in this diagram. Okay, we have this wideband receiver. So this is being enlarged. What happens in the transponder? Okay, is this. So then the low noise amplifier is fed into a mixer stage, which requires a local oscillator signal from the frequency conversion process, and a second amplifier will follow the mixer stage to provide an overall receiver gain of 60 decibels. So this is the input to your demultiplexer. I should rotate it. Just a minute, I'll rotate it. We have the match terminations. We have the redundant receiver, the same specifications. We have match terminations, and it is being divided into 12. 1, 2, 3, 4, 5, 6 in one, with one match terminator, another 6 with another match terminators. We have 3 decibel coupler, and it is sent to the receivers and then to the corresponding channels with odd and even fashion. Okay, so this is the input to your demultiplexer. So coming to the next slide. Next is your power amplifier. So what happens in the power amplifier is that the signal obtained into the system, where one is your input filter, 2 is your wideband receivers, 1 is your receiver, another one is your redundant receiver, and 3 is your 3 dB coupler, 4 one is your demultiplexer, 5 is your attenuator for lower positioning, 6 is your amplifier, 7 is your multiplexer again. So in the power amplifier, the power is being amplified at a number 6. The power is being amplified from 48 decibels to 104 decibels. So amplification occurs here. So this is a schematic of a traveling wave tube and power supplies that is used in satellite. Okay, so this traveling wave tube is similar to what you are studying in your microwave engineering. So that traveling wave tube antenna is being fed in the satellite for efficient supply to your satellites to rotate. So we have a power supply, we have a heater, cathode, followed by the gridding. All the power which is being generated to is attracted towards your anode in a single structure through magnets. Magnetic furnaces on both the ends will make it a spiral shape, and it is being collected to your collector. And when the power is being given, it takes a spherical path and it moves towards the output power. So taking a helical path. Okay. So the power amplifiers always. Sure. Why do we go for this TWT? Is that the power amplifier uses is your TWT. So the TWT are widely used in transponders to provide the final output power required for the transmitting antenna. So we have an electron beam gun assembling consisting of heater, cathode, focusing electrodes to form the electron beam. A magnetic field which is confining the beam to travel along the inside of a wire helix. And for high power tubes, the magnetic field can be provided by means of a solenoid and a DC power supply. Then the power system. The advantage of using this TWT is that it can provide amplification over a wider bandwidth. Approximately it can provide for 2000 megahertz. So this TWT may be called on to amplify 2 or more carriers simultaneously also. So thereby it is referred as multi-carrier operation. So the large size and high power consumption of solenoids make them unsuitable for abort satellites, whereas low power TWTs can be used or deployed in satellites. So next comes the antenna subsystem. So most probably all are familiar with the antennas that are present in satellite. Antenna provides dual function. One is uplink transmitting, uplink receiving, and downlink transmitting. Uplink is from earth station to satellite, and downlink is from satellite to earth station. So generally this is used for telecommunication purpose, broadcasting high directional antennas. So in antenna subsystem, directional beams are usually produced by means of reflector types antennas. So where they use a parabolic reflector antenna with this specification. Since you had studied in depth about all the antennas and propagation, I'll skip this derivation. Okay, so this is your parabolic reflector antennas gain. That's all. Okay. The polarization takes place in a device known as orthocoupler or orthogonal mode transducer (OMT) in antenna subsystem of satellite. So in comparing the C band and KU band, the largest reflectors are used for 6/4. We use large reflectors we use 6 gigahertz as uplink and 4 gigahertz as downlink. And if you use small reflectors, we require uplink of 14 gigahertz and downlink of 12 gigahertz. So this 6 bar 4 represents your uplink slash downlink. 14 bar 12 is uplink slash downlink gigahertz frequencies. And the satellites used for mobile services in L band employing much larger antennas. Okay. So this is your structure of your antenna subsystem. The transmit and receive signals are separated in a device known as diplexer. You can see hemizonal transmit reflector, hemizonal transmit feed, east spot, globe horns, west spot, hemizone receive reflectors, hemizone receive feeds. So this is just an example of antenna subsystem that is used in satellite for transmitting and receiving your signals. So with this, I complete my presentation. Any queries you can put in chat box.